Hello there, this is Daniele from Toolchefs, and in this video I'm going to give you a demo of AtomsUnreal. So the purpose of this video is to show you some of the main features that we have in AtomsUnreal. We're not going to go through all of them, but if you are interested to know more, there are, we have more YouTube videos on our channel, and also you can find more information on the documentation, as well as, if you want to, if you have questions, you can also write to us directly at support@toolchefs.com, or you can write on our Google group and we'll reply as soon as possible. So in today's videos, we're going to use a content that we also uploaded on our website. So if you go on our website and you go on the download page, after you have registered, you accept the terms of agreements, you'll see here these two new projects for Unreal. And we're gonna see both of them in this video. So the first one is the demo project, the one that we're gonna check now. And then we have the shooter demo that Alan is gonna explain to you later in the second part of this video. So I would encourage you to download them both, and you can install the plugin, the AtomsUnreal plugin in Unreal, request a valid license, and then after that point you can check this project basically. Okay, so here we are. In this content here we have prepared some maps. So we have the maps here in this map folder. Before going to the maps, I'll explain briefly how you can set up your content so that it works with Atoms. So of course you need some assets. In the content here we have some assets that are already being prepared for you. In particular, we have the man, and also we have another agent type, which is the boy. In here, you'll find that we have these 80 man and 80 boy, which are basically agent type assets. An agent type asset is a combination of a skin asset, which is basically just a skeleton mesh, a skeleton asset, which is an Unreal skeleton, and also you have to provide a valid name, which should be unique for your agent types that you have in your content. Then we have a scale multiplier that can be used for multiplying the scale of all the agents having this agent type. And then you can also provide a state machine, a character asset, which is used for for the real-time retargeting that we have in Atoms. And then we have, you can provide also some collision shapes for the collisions, and also physical assets if you want to use ragdolls. So basically, let me show you. So for the skin asset, I said that this is a skeletal mesh. Is not completely true, but if, for instance, if you go and check that this asset, you see that this is actually is this asset here. This is actually an agent variation asset, which is basically a collection of skeletal meshes, because you can, in Atoms, you can create these variation assets, like add like a combination of skeletal meshes, and then use those as the skeletal mesh for your agent type. Then here also you can provide attachments if you want, and basically this is how you define the agent type. For this stuff, we have again other videos on the YouTube channel. You can check those if you want to know how you can set up your own agent type. Just to go briefly through all these assets so that you have an idea during this demo. On the skeleton is a very simple Unreal skeleton, but what we did here is we provided some the Atom skeleton user data. This user data actually defines and tells to instruct Atoms which are the pelvises of your skeleton, which are the legs, and if you have any extra joints metadata that you want to attach to your skeleton. For metadatas and also how Atoms works, we have also a video which is basically the Atoms crowd overview that I would actually encourage you to see if you are going to be using Unreal, because as in Unreal you can go really deep and do a lot of things with Atoms. Having a look at that video first will give you an understanding about how Atoms works and how you can interact with it. So you need to provide this information, especially the pelvis. The pelvis must always be provided, otherwise Atoms just tags the first joint in your as a pelvis in your skeleton. But you have to provide these joint names, for instance, for the pelvis, and then for the legs and so on, if you want to have a terrain adaptation. If you don't provide this stuff, basically this information, Atoms won't be able to adapt your agents on a terrain. And the legs, you have to provide the legs if you want to have also the foot locking system activated. If you don't care about that, for instance, if you are just developing a game and you don't care about that, because that of course is gonna give, like it's gonna hit the performances if you use this in a game with a lot of agents, then you might just want not to define any leg and just provide a pelvis. So this is how you define your skeleton for Atoms. And then here we have also a bunch of animation clips that have been created for you. If I open, for instance, the main idol, we see again this is just a simple animation sequence from Unreal. But what you can do here is also you should actually provide an asset user data called Atoms and clip user data. And this user data contains all the information that Atoms needs to know to use this animation sequence with Atoms. So we have a loop start and end frame, the blend between that is used between the looper start and the start frame when the clip is looping. Some frames that instruct Atoms about how many frames you want to use when the Atoms exit the foot lock state, when it's being adapted to the ground, and basically it's blended to the current pose from the clip. You can tell it to Atoms if the clip is loopable or not. You can disable the foot lock from here. We have also you have to provide a direction for your clip. And then we have the clip velocity if the clip is in place. So Atoms is quite different from other crowd engines because Atoms doesn't use a particle and then attach the skeleton or your agent onto a particle. It actually simulates the skeleton during the sim. So for instance, let me actually open the walk, because it's gonna make more sense. You see that the clip is actually moving in space. So in cases where you have a clip that is is animated in place, so if you have for instance the mannequin clips, they are walking in place, then you have to provide a clip velocity. So in this case it's 0 because our agent is just walking, so we are getting the velocity of the clip from the motion of the agent. But if you have an in place again animation, you would have to provide the velocity, so that basically then Atoms can use a constant velocity during the sim. You can provide also compatible agent type, which is used if you are going to be using the retargeting animation system from Atoms. And also if you're going to use a bunch of things here like the mirror or reverse, and also I think the perching, and yeah, I think that's it for now. Also you need to also provide the compatible agent type if you are planning to use the additive clip, and if you're gonna, I think one of the modes is the bind pose, so it knows basically where the bind is coming from, the bind pose is coming from, and I think that's it. So you can then again we have a video that will explain to you how you can set up your animation clips, and I would encourage you to check that. But basically this is what you have to do for setting up your agent types and animation clips. And finally we have some more assets, for instance state machine. The state machine is a very standard state machine, but it's not as complex as the Anning graph from Blueprint that you can use from Unreal. This basically is just a graph telling Atoms how how you can transition from a state to another. So you see we have connections here. Each state can have multiple clips, and then from each clip can have like a merge type, so it can be merge, exclusive, or random. So depending on when you enter this state, if you want to randomize all the clips that are within this state, you should set all the merge types to random. If you set exclusive, the first clip that has an exclusive state will be played, and the merge is just gonna merge them all together. So you want to use basically a state machine if you want to blend the animation, and have your agents maybe that they start working and then they maybe start running after a certain amount of ticks or things like that. Then you can provide the blending out frames for the blending, and there are a bunch of other options here that we're not going to go in details because we have other videos explaining this. Another thing that you can do after you connect your states is also you can provide transition clips for the connections if you have any. This is mainly for traditional VFX workflow. If you are making a game, maybe you don't care that much about having transition clips because you're just happy with just having a linear blend between states. So yeah, basically this is how you can also edit the transitions. and then you can provide also, of course, blend in and blend out frames for the transition. And finally, if we go down here, we have the variations. So a variation is basically a set of, let me open one. So you remember before I showed you the variation asset. So it's a combination of, of skeletal meshes. And in Unreal, what you can do is you can provide for each agent type, you can provide a set of variation that you can use, and then they will need to have a name. So we have an example later where this will make more sense, but this is basically how you define the variation. You manually would have to define all those variation assets. You can then append them here to your variations list, and then provide a name for each one of them. Okay, so once you have your assets ready, you can start creating an agent group in your scene, so that basically you can create agents and lay out your simulation. So you can go in place actors and search for an agent group. I'm just gonna set the location to 000, although that is not necessary. And then once you have your agent group, basically this acts as a container of your agents, and all the agents within this agent group will share pretty much the same behavior. You can define particular behaviors for specific agents if you want. We're gonna check that out in a second. So having the agent group selected, you can click on add component, and then if you scroll down in this list, you see this section here, Atoms behavior. So these components are all the behaviors that are available by default with Atoms. You can create your own with Blueprint or C++ if you want. But usually what you would do is you would start by creating a layout behavior. You can also create agents with Blueprint if you want. We're gonna see later how. The grid layout is basically one layout that just creates a grid of agents, so it's pretty simple. You can just select your agent type here. So we have the man, and you can provide a size for the grid, so say 3 by 3. And then we can say you also to attach a state machine. So the state machine, what it will do, the state machine behavior is gonna go inside the agent type definition. So it would be here. The agent type definition says that the state machine is this asset here. So it will basically build internally a state machine that will work for each agent. So if you go down here, you see state 0. So this is the idle state, and that's why all our agents are in idle. If we press 1, if we change it to 1, they're gonna walk. 2 is jog, and 3 is run. You can also, of course, change the the state during the simulation. So you can go from 0 to 1. Actually, all these, let's see, all the states are connected to each other. So you can go from idle to walk, walk to jog, and so on. So you can go from one state to all the others. Okay, so that's great. And in pretty much all the modules, you will find for the properties, these like the same name of the property, but with like another property, with the same name of the property, but ending with override. When you find these kind of properties, means that you can override this property per agent. So if, for instance, if I go in here and then I select, say these 3 agents here, and I set to 1, and set value, you see now we have changed this state to 1. So these agents are now working. And so that's why we say that you pretty much end with the same behavior, because you can, of course, edit the simulation so that each agent can look differently. So this is a way which you can do it. You can also, we can also provide an hide field. Usually an hide field is defined by providing a collision channel. So if you go here, so it's a trace channel. We have added this atoms ground. If you go on the floor, this floor should have the collision. If you go collision, I think it's on default, yeah, but if you go for this as custom, you see that atoms ground is automatically selected. So anyway, if you see that your agents are not adapting to your terrain, you have to make sure that the collision channel is activated for your ground mesh, basically. Okay, so that's great. Let's go back to default. So we have another video that we just published that also explain more in detail what you can do with your agent group. I don't know what happened here. I think I just pressed. Yeah, I think I duplicated the agent group by mistake. Let me just 3 by 3. Anyways, the same thing that we did before. So atoms ground. Anyway, you can also activate the node overrides here. So okay, so this is basically how you can define your initial layout with a grid layout, and also attaching some animation. And then what you could do also, you can start changing the direction of the agents so they just don't work straight. So for instance, let me just increase the scale of this a little, so it's quite a bit bigger. And then we go in the agent group. Let's change the state machine to behavior to 1, and then we do we can say, for instance, follow curve, and we can create a spline with Atom spline actor, drag and drop it here. Sorry, I'm gonna select this, move it, alt drag, and create a new vertex, and then alt drag, and I'm gonna create another vertex. So once we have the spline, we can go in the agent group, follow curve, Atom spline actor, curve weight is 1. Anyway, we're providing that curve, so now the agent should turn. You see now they're turning and following that curve. Anyway, this is a very user-driven approach, but you know, like, you have to provide the curve. But again, you can change the sim and the direction of the agents and a lot of other stuff about the agents with the you know, metadata modules, and also with Blueprint and C++. Another thing that you need to know, again, is explained in the overview video. But basically, each agent is independent from each other, so they have their own independent network of nodes that basically computes the posts at each tick. And also what they do is they have a set of metadatas that basically drive the simulation and also edit the behavior, or you know, edit their look, or maybe they're just, you know, metadatas that you use for you know, actually during your inside your behavior. Then you have to, you know, like, you do something depending on which metadata each agent has. Okay, so this is pretty much how it works. The last thing that I'm gonna show you, let me just create a new agent group and delete these two, not that one, group, agent group. The other thing that you can do is you can also have you can also lay out agents in a more artistic way. So let's say we have the points layout behavior, which is basically the layout that lets you do this like artistic layouting. Then we attach again a state machine behavior. If we go here in modes, we can find the agents atoms layout tool. And if you go, and if you have an agent group selected with the points layout, you can click on the placement button and you can start placing agents around. So, and this is basically a more artistic way than the curve, you know, like just having a grid and you know, or even using a mesh scatter and so on. So you can, you know, start clicking around, and we have different distributions. You can set these parameters by changing here the, you know, for instance, the Poisson mode, the max number. So we can say maybe 100. I think it's num sample. Yeah, the radius can be maybe 400, something like this. Anyway, so basically this is how you can you know, use also different distribution. You have the polygon, so you can click around, and you know, you can, after you add 4 vertices, you can then create agents and click place agents, and now we have those agents in our scene. You can use a curve, a mesh scatter, and so on. Then once you have placed your agent, you can still go in here and, you know, move them around and so on. So the cool thing about this is that you can, you know, place agents quite quickly on any ground, and it's quite quick. So you can even delete agents if you want. If you don't want to have those agents anymore, select more agents and move them around, or even rotate them, you know. You can also use different rotation space, but also for this tool we have other videos, and you can also edit caches if you want with the layout tool with the sequencer. Okay, so that's cool. Let's now jump on the maps that we have prepared. So these maps is basically what we're gonna see and what we will find in your demo. So in the demo content. So first of all, let's start with the retargeting, which was like the initial map that I had open. So basically here you see we have it's a pretty simple simulation. We have just a grid layout and a state machine behavior. The grid layout has a default agent type demand, but also we have created an override for these agents. So all of these are boys. So why is this interesting? Because if we go here and we go in maps, sorry, not maps, in assets, man, and then we go agent types and then the boy, we see here that the boy has its own assets for the skeletal mesh, the skeleton, and also the characterization. But it's using the same state machine as the man. and the man is using actually clips that are for the man, so the skeleton is different. You see here the character as basically here what's happening is we have a real-time retargeting that is happening during the simulation, and this is possible because we have this character asset being set up for both the boy and the man. So if I open the agent type for the man, we also have his own characterization. These characterizations can be created, so if you go in them and check, like they're pretty hard to read because they're quite quite a long list, but you can create these ones directly from Unreal, from Skeleton Unreal, and Unreal Skeletons. So you can, we have a video for this stuff as well, so I would encourage you to check that in order to understand how you can create those character assets. But for instance, if we press play now, we see that the agents are working, and see the clip is actually adapting to the skeleton. The velocity of the clip is being adapted to the boy, so you see it's going actually slower than the man. And so if you have characters of different proportions, then you can start, having, animations coming from a zombie character going to a standard character, or maybe a shooting clip being applied to different kind of skeletons. So this is great. The only thing that you must be aware is that the Atoms retargeting is happening at real time, so at runtime. So what means that of course the simulation will be slower, especially if you have a lot of characters which are having this retargeting system being applied to them. So if you are making a game, maybe this is not the best and if you want to have like a lot of agents, maybe this is not the best solution for you. You might still want to have specific clips for each specific agent type. But otherwise, you can if you don't have a huge amount of agents in your scene, and then you have you are happy with this with the performance that you have with real-time retargeting, you're very welcome to use it. Okay, so let's go back to the next. So we did the retargeting. Now let's have a look at the area trigger. So we said before that actually first, let's look at the terrain adaptation. So for the terrain adaptation, we just saw earlier that it's just quite simple. What you need to do is just to provide on the state machine the height field name, and this is like a trace channel that we set up already in this project. So if we go in the landscape and we search for collision, we see that it's on block all, and if we go down, Atoms ground is activated, but anyway, you could even go on custom and check it if it's not activated. So anyway, if we press play, we see here that the agents are jogging and they're adapting to the terrain. And as you can see, there's no foot sliding. It is because we have our locking system activated. And yeah, basically they're adapting to the terrain. So to adapt the legs to the terrain, we'll also apply a soft decay and a stretching for the legs, so that basically the animation still looks good. Okay, so this is the terrain adaptation. With the area trigger, we also added the terrain adaptation. That's why I wanted to jump back to the terrain adaptation so that we don't skip that specific. We didn't skip that specific example. But for instance, for the area trigger, what's happening here? So we have another module that is called area trigger. And in here, what you can do is you can provide a mesh. So we provided a plane. And then you can provide a name for a metadata that you want to edit. So in this case, I think it's state. And then we change the metadata. So we know that the state metadata is an int metadata. You can check the type of the metadatas on our documentation. We have a metadata list of all the metadatas that you can change. So for the int value, we'll change it to 2. So it means that the agents from a walk, so they are actually walking now because their state is 1. They're gonna start jogging as soon as they enter this plane. So again, this is what I meant before when saying that the metadatas can drive a simulation. Well, because the state machine actually uses this state metadata, which is the same thing that is changed by this property here. So the state machine get this by the value of this property, and then sets the state metadata with this value. Then we have the area trigger that is just overwriting that value and setting it to 2 whenever they are getting inside this inside this plane. So if I press play now, the agents will start jogging. and then as soon as they get out, they start walking again. Okay, great. So that's the area trigger. Then what we can look at now is maybe you can look at the navigation mesh and avoidance. So in Unreal, you can use the navigation mesh, the standard Unreal navigation mesh. In this agent group, I have mesh scatter that is using the navigation mesh for generating the agents. And then it's using, I've attached the navigation behavior, saying I want the agents to go to a random point on the navigation mesh. And then also I want them to avoid each other. So I just used the PetVO algorithm with agent avoidance to basically make them avoid each other. So if I press play, we see the agents are walking around, they're avoiding each other, they're avoiding the obstacles, and this is thanks to the navigation mesh that is implemented in Unreal. So yeah, basically this is how you can populate. If you have a very simple setup, agents walking around, maybe in a city, you can set up your navigation mesh, set up the avoidance, and then they can just avoid each other. Cool. Okay, so now let's have a look at the variations. So in order, you noticed earlier in all the examples, all the agents look the same. And for variations, what you can do is, for the agent groups, what you can do is you can also change the variations of the agents. If you go on the agent group and you scroll down, you will find this view mode, which is set by default to variation. But if no variation is set, we usually just display the skin mesh, which is this one. If instead you use variation and you provide a variation asset, so this asset in particular is this one, the one that I was showing you earlier, which is over here, then you can start attaching variations on the agents. Again, if you noticed here, we said before that each variation has a name, like that. And in here, I have a variation module that has some overrides, and you see that each agent has its own different, variation name. So color variation there, casual somewhere one, and so on. So let me clear the selection. Oh, sorry, I did that by mistake. Anyway, yeah, so we have a casual summer one, we have the casual summer color variation, and so on. So if we are more, if we check again the variations, we noticed here that this mesh is, so this variation is a combination of these meshes, and this combination is this variation is a combination of these meshes, and then we have this other one, which is basically, so each one of them have different kind of meshes and materials applied to them. So that's how you can achieve mesh variation. But also you can, in Atoms, because we want to have very high performances, what you can do is you can change the look of your material by passing some look of your mesh, by changing the material with some metadata that we can pass from the agent to the material itself. So in this case, what I've done is I've created a t-shirt color metadata with that metadata module. I've set the type to vector, and if I go here in vector, vector value, if you see here, we have some overrides just for those agents here, which are basically is a vector that where the value is between 0 and 1 for all the values of the vector. So basically what's happening is I've set up this for the variation of this, for the mesh of this variation. So in particular, it was this is the variation and this mesh here. I've set up a special material. We notice that here we have a particle color node that is reading basically these metadata that we have applied here. So the metadata is again the t-shirt color, and now we're passing this t-shirt color to the material is by in the per instance metadata section on the agent group. We're just setting the same name of that metadata, and basically to the material you can pass up to 20 floats. So the first 4 are going to be read by the particle color, then the others are going to be read by the dynamic parameter. I think it's this one, yeah. And then basically you can read the other 16 floats from these with this node. So we have already again another video explaining how to do this stuff, especially also if you want to start using hero promotion, which is another feature by Atoms. Then you need to use even a different setup if you want to have the same material working both for for the hero converted characters and the standard agents. So anyway, in this case, what's happening is we're just a base color which is white, and then we're just multiplying that color for the color that we're passing through the metadata, and that's why basically we are having this different look for the t-shirts. So pay attention. What you can do this also if you have just the plain. Let me go back to the agent group. Is this one? Yeah. If you, for instance, have just the skin mesh, you don't want to have any variation. You're just happy by randomizing the color of the t-shirt of the skin mesh of the t-shirt of the man here. What you can do is really you can go on the where is man agent type and get the man. Say yeah, this is the material. What you can do is here is just create a multiplier here and get the particle color, and you could do basically the same thing by just using these materials. So okay, so that's how you do variations. Then we have let's go back to the maps. We have the sequencer. So of course we support the sequencer because it's pretty important. So if you go in kinematics, and we're gonna open that sequence, which is basically here, then you see that here we have what we have done. We have drag and drop this Atoms agent group into the sequencer, and then here we have activated the use static frame option. Here the reset frame is not set, but it's always best practice to set it to 0 because you want this reset frame to be the same as the start frame of your sequence. So in this case, in my case, it's 0. But anyway, if your sequence starts at 1001, then it's good practice always to set the reset frame. And then basically you have to create a track for the static frame, and this track is basically what drives the value of the static frame here in of the agent group. If I press play, you see that the simulation is running smoothly. So this is actually live simulation being played by the sequencer. But if I jump from frame to frame, you see funny things are happening, and this is because we are simulating. So you need to go frame by frame to see the actual look of the simulation. You can jump between frames if you cache out the simulation and then re-import it in Unreal as a cache, and then you can start jumping around with the sequencer. You can start jumping frames and so on, and that is basically totally allowed. Another thing that you can do with the sequencer is you can also override the parameters that you have here for each component, behavior component. So what you would have to do is just create a new track and select the whatever behavior that you want to add here, and then you can just attach another track for the property that you want to override. So in our case here, what we're doing is like we're just changing the curve weight during the simulation, and then we're also changing the state. So I think the agents are gonna stop following the curve after a certain frame. So they're gonna keep the last direction that they got from the curve, and then they also start walking and changing basically from jog to walk. So this is what you can do also with the sequencer. One thing that you have to be careful is that if you use the use static frame option and you press play, the simulation will always look stuck, because basically what's driving the simulation now is not the tick anymore, is actually the static frame value here that we have here. So this needs to change at every frame if you want to, at every tick, sorry, if you want to have the simulation being updated. So anyway, you have just to activate the use a static frame option only when you're using the sequencer. Okay, that's great. Finally, the last example is the blueprint behavior. So we have prepared this little blueprint behavior for you. It's pretty simple, but it's just useful to show you how you can, certain things that you can do with Atoms. So if we go here and we check the agent group, we see we have just two behavior, and we don't have a layout behavior. This is because the agents are being created by the demo blueprint behavior. So if I go here and let me go and find class, and it's basically the blueprint that is defined here. So you see it's pretty simple. Actually, let me press play first so we see the simulation. So we have these 10 agents that are just walking in a circle. And if we just exit for a second simulation, if we go in that blueprint, We see here that we have we've created two overrides. So we have the two functions that are being called by Atoms during the simulation. So the first one is the init simulation that is called at the beginning of the simulation, and then init frame, which is called at every tick. Before the agent computes its pose. So if you go here in overrides, you see here we have some other events that you can use. For instance, here we have the agents created, agents killed, begin play, end frame, end play, and so on. So really depending on what you have to do, you can do some things, and then Atoms with the blueprint, and then Atoms will create agents or maybe change the direction and so on. In this case, what I'm doing is like we have this for loop at the beginning of the simulation where we create just 10 agents in a row, and you can use then the initialize new agent blueprint for a node for creating the agent. You can provide the type of the agent type, and you should set -1 here if you want to have the group ID being assigned by Atoms by default. Otherwise, you have to provide a valid group ID for each agent. And then during the init frame, what's happening is like for each agent, we're just looping through all the agents. We're getting the direction metadata, which is the metadata that defines the direction of the agent at every tick. And we're just rotating that vector around the z-axis. And then we're setting back that metadata, so that basically that's why we are seeing that the agents are just walking in a circle. Although this example is very simple, you can really do a lot of things like create your own avoidance, create your own go-to navigation system or things like that, and then integrate that with Atoms with Blueprint or C++. So this is all for this content. You can again download the other content, the shooter demo content from the website. And now I'll pass the ball to Alan, who is gonna explain to you that content.
The Atom Shooter demo is a showcase of the new feature of the AtomsUnreal 2, mainly the new behavior tree. The drive the agent here to make complex behaviors and let the agent interact with the player. Let's search for navigation path to reach the player or to do some patrol logic. And also there is also some logic to run dynamics on the agents and so on. So let's have a look to this project. So this project used a couple of animation sequences from the admin starter pack. They are just basically idle, jog, some locomotion, fire shot clip, and all those clips are standard running sequences with some setup made for Atoms. Usually just loop range, direction, speed, and a couple of more attributes. Then on the Atom section, we can see the agent type setup. So in this scene, we have two agent type. One is using the mannequin, and the other one is using the gun as a separate agents. And since in Atoms we can basically constrain and create a hierarchy between different agents, and there is some module that synchronize parent and child agents. In this case, for example, the weapon is a separate agent that are constrained and synchronized with the parent mannequin. So let's look at this standard state machine, sound locomotion, also the fire clip, and then let's go to the main agent group. So there are two agent groups. So one agent group, and that this one create the mannequin agents. This one using the mesh scatter layout that just scatter agents on top the navigation mesh in this case. So it's generating 500 agents in this scene. And then there is a state machine that control the locomotion of the agents, ragdoll that control the capsule collision and the ragdoll physics, and then some other avoidance and some other modules. And then there is a behavior tree that is the one that drive the AI for the agents. And then we have another agent group. The agent group is using a sync module. The sync module basically synchronizes agents between a parent and a child agent group, creating a parent-child relationship between the agents. Also do constraints between the parent agents and the actual agents. Also synchronize metadata and animation. In this case here is set up in order to create a constraint between the hand of the mannequin with the root bone of the gun, and then it synchronizes all these metadata to synchronize the animation, like the fire tags for the animation, also hero promotion. There's some other metadata, and then there's a behavior tree here as well. This behavior tree is basically used to handle the logic to spawn the projectile from the weapon. We can have a look to the behavior tree here. So this behavior tree is an Atoms behavior tree. Atoms can run behavior tree that are a bit different from the real one, because each agent has its own tree and it's run in multi-threading. So a group of agents using multiple threads compute its own behavior tree. And this one is a really simple behavior tree with some conditional to check some condition. All those blue nodes here are decorators, and then there is also a custom blueprint task. This blueprint task basically generate new projectile to emit from the gun. In this case, it's just filling the new position. This new projectile that is an array containing transform for the new projectile to create. In fact, if you go on the weapon group, we have inside the percent frame that's called after Atoms compute the pose of the agents, iterate over the new project to emit, and then you spawn for each projectile position on your projectile. Okay, let's go back to the enemy group. So the enemy group has some logic for collision. So it implements the event hit. The event hit basically control if an agent is hit by a projectile that is spawned by the player, not from other agent. So in that case, it discards basically the hit condition. Then from the hit, you get the actual agent ID here, and also decrease the health metadata. And this metadata also is used to drop the red color on the agents when it's hit, basically. Every time it's hit, the health is decreased here from this code. And then when it reaches 0, it's triggered the ragdoll. So you generate the ragdoll, activate the physics simulation, add an impulse as well, and then as well the ragdoll is activated on the weapon as well. This way the sync module just breaks the connection, the two, and the weapon is simulated physically. Now let's have a look to the main logic, so the behavior tree. So let's open the behavior tree. So in this tree there are three main action that handle. So one is the patrol action that is handled by this branch. And it's basically a sequence. So there is this these tasks that generate a random point over the nav mesh in a certain radius from the agents, and then after the agent found a valid target, is switch to the run state, and then they go to generate a navigation path from the navigation mesh, and the agent will follow this navigation path to reach the target. After reach the target, then go in idle state and then wait sometimes. Then there is visible decorator. So basically, this patrol behavior is executed until the player is not in a certain cone angle and distance from the agent. From the agent. In this case, basically, when the player is visible, that this branch stop immediately and then go to the attack branch. This attack branch, using basically an active selector to basically select and check dynamically every condition, every branch here. So basically, it first check if the agent is in a certain distance from the player, then start the attack sequence. So here, basically, it changed to a fire state inside the state machine. Also orient the agent towards the enemy, the player. And instead, if the player is at this distance, the active selector block the computation of this branch. So, for example, if the player is far than this other distance, and then it's basically called this sub branch that just basically try to go at the player location. Then basically, if the agents go far than this distance, then the active selector just stop the attack mode, and then the agent go back in the patrol mode. Then there is this other branch. This other branch control the hit animation when a projectile hit an agent. So when an agent has been hit by this projectile spawned by the player, it will be basically trigger this branch, and this branch basically just check the hit condition that is set by the blueprint logic from the hit event here, and then also set the attack mode to 1, and then it plays this hit animation only on upper body of the mannequin, so from the spine from on top. And then this tree is continuing running during all the simulation. There are some small tricks for optimization. For example, the Q2 doesn't sample the nav mesh at every tick, but there is a specific frequency. So when it computes the path, it saves the path in this curve, and then later the next tick it uses this curve instead to calculate a new path. And this way, here in this case, we are compute a new path every half seconds. Also, all this behavior tree is written by this blackboard. The blackboard in Atoms is similar to the real blackboard, but we have some more option for the metadata, because you are able to link metadata to a blackboard key. For example, this one linked the position metadata of an agent to this key. So this way, the behavior tree can basically access the metadata directly from the tree. Every attributes on every node in the behavior tree can be connected to a Blackboard key. This way you can control everything dynamically. For example, here you can see and switch to a Blackboard key mode and connect a Blackboard key. Okay, in this scene there is also another feature, that is the hero promotion. Basically, in Atoms you can promote agent from the instance agent to a actual scatter mesh. Sorry, skinner mesh. In fact, if I put a pause here and I go to the enemy, let's select the weapon thing. So as you can see, this one is our instance and meshing component that using GPU instancing, but then there is also promoted agents. Those promoted agents are promoted based on metadata. So you can promote an agent to a specific, to a hero, and then promote back basically the agent to the normal instance component. On the promoted agents, you can run ray tracing. You can have more targets, also better shadows, because the bounding box of a single agent is smaller compared to the full agent group. In this case, if you need more details, shadows, or I don't know, ray tracing, reflection, and so on, you can do that quite easily. So yeah, that's mainly all the main feature that we use in this demo scene. Let's try it. You can download from our website and try on your machine. Thank you for watching.